Okay, perfect. Hello everyone and welcome to our 98th free webinar. Actually, this is a result of a collaboration between OPA Energy and Geology Works. Our webinar titled SEM-EDS Analysis of Materials, Investigation of Calcite and Dolomite, presented by our instructor, Ms. Telly Hamzayeva. She is a junior researcher at the Institute of Geology and Geophysics. She specializes in geochemistry and analysis with a focus on energy dispersive spectroscopy for mineral characterization. Her work contributes to a better understanding of the chemical and structural properties of various geological materials. She conducts seminars at Baco State University in the Department of Mineralogy and Crystallography, specializing in the subject of nanomineralogy and geochemistry. Welcome, Ms. Tilly. Before we start our session, I'll just make a small presentation about OPA upcoming services and plans. Here is our next live course that will start next Saturday. Actually, not the next Saturday, it will be the after next one on 5th April, titled Well Completion. You can scan this QR code to register. And we have completed more than 50 recorded courses, which is 50 live course, which is now available as live of recording sales in different disciplines like reservoir engineering, G&G, rig and rigless operations, production technology, safety and analytics bundles. Not only this, but we have also offered Ramadan discount. You will enjoy 50% discount on all our recorded courses. So all these prices are before discount, so you can apply 50% on them and enjoy our courses. Visit our website, add your courses to the checkout cart, and add this coupon code, and you will get the 50% discount. You can simply access our website by visiting www.opacourses.com or just scan this QR code. I will also share it in the chat box. Here is one of our best services, which is mentorship program. It's a one-to-one mentoring sessions. It's like a tailored program based on your needs. Your request can include practicing on how to produce output results from software, guiding on personal data of the mentee, professional guiding for PhD and master, and helping undergrad students in their projects. We have completed more than 45 mentorship program with more than 900 learning hours. You can also scan this QR code to register in our mentorship program. And as I've said, here's a glance of our website, www.opacourses.com, where you can access every single service from OPA, whether they are recorded course, live course, enroll in internship and mentorship, or accessing our free webinars. So make sure you pay it a visit. And finally, how to be an OPA ambassador. There are two tracks. First one is to take one or more course. The second one, or just take a mentorship program. So what will you get from being an OPA ambassador? You will get discount on all courses and group discounts when you invite your friends with you. Thanks for asking, and now it's time for our session. Ms. Telly, the mic is yours. You can share your presentation now.
Thank you. Okay, as I see now, is everything okay with my presentation? You see it?
Yes, it's clear, but if you can open it as a slideshow, it will be perfect.
The slideshow. Okay, fine.
Okay,
Now it's
perfect.
okay.
Yeah, it's clear.
Fine. Hello everyone, my name is Telli Hamzaeva and today I will presenting an in-depth analysis of calcite and dolomite using scanning electron microscopy, SEM, and energy dispersive spectroscopy, EDS. This presentation will cover the principles of EDS analysis, structural and elemental differences between these minerals, and how these techniques help in material characterization. Okay, let's begin. I would like to show you presentation overview. First of all, we'll look at the SEM operation, how scanning electron microscopy works. Next one is EDS analysis, explanation of energy dispersive spectroscopy and these principles. Next one is calcite and dolomite, basic characteristics of calcite and dolomite, and table comparing properties. 5 is dolomite composition, elemental analysis via EDS, and next one is calcite composition, elemental analysis via EDS, summary, brief review, what we done, and in the end, we will have interactive question. Here is the slide which show you how does a scanning electron microscopy work. A scanning electron microscopy appears using several key components. An electron sources, it's here, an anode, a condenser lens, and coils. In the end, it has objective lens. It all starts with the electron source, which generates electrons at the top of the microscope's column. These electrons are then attracted to the anode plate, which has a positive charge, forming a focused electron beam. Next, the condenser lens comes into play. It controls the size of the beam and the number of electrons in it. A smaller beam means higher imaging resolution. Apertures can also be used to fine-tune the beam size for better precision. The scanning coils then deflect the beam along the x and y axis, making it move across the sample surface in a raster pattern. Finally, the objective lens, which is the last lens in the sequences, focus the beam into a tiny spot of the sample for detailed imaging. So interestingly, that as you see, since electrons cannot pass through glass, SEM lenses are electromagnetic. They consist of wire coils instead metal poles. When an electric current flows through these coils, it creates a magnetic field, which in turn precisely controls the movement of the electron beam. Let's go. What is EDS analysis? EDS is a powerful technique used to analyze the elemental composition of a sample by detecting X-ray emitted when it is exposed to an electron beam. Here, how it works. When an electron collides with an atom, it knocks out on an electron from the inner shell, creating a vacancy. Electrons from higher energy levels then move down to fill this gap, releasing X-rays in the process. Since every element has a unique X-ray signature, this allows for quick identification of elements presented in the sample. from beryllium to californium. Not only can EDS determine which elements are presented, but it can also measure the intensity of the emitted X-rays to estimate elemental concentration. Additionally, it enables X-ray mapping, showing the spatial distribution of elements within the sample. Modern EDS systems go even further, providing real-time chemical imaging, meaning researchers can observe elemental compositions dynamically while adjusting sample setting or positioning. Principles of EDS analysis. EDS, energy dispersive X-ray spectroscopy, appears based on the principles of characteristics X-ray emission. When a sample is bombarded with high-energy electrons from an electron microscopy, commonly SEM or TEM, it absorbs energy and ejects electrons from its inner shells. As electrons from higher energy levels move in to fill these vacancies, they release X-rays in the process. Each element has a unique electron structure, meaning the energy of the emitted X-rays is specific to the element that emitted them. By detecting and analyzing these specific X-ray energies, EDS can identify the elements present in the sample and also quantify their concentration. Here is the pictures of principles of EDS analysis. In EDS, X-ray detectors capture the emitted X-rays, how I said before, and convert them into electrical signals. These signals are then proceed to create an elemental spectrum. This spectrum displays peaks at specific energy levels. Here you can see. Here is the peaks, and each of which corresponds to a particular element. This process allows EDS to provide both qualitative and quantitative data. What sets EDS apart? It is ability to study the spatial distribution of elements at the nanoscale, making individual tools for understanding the complex structure and composition of biological samples, for example. Basic characteristics of calcite on dolomite. Let's talk about two minerals, calcite and dolomite. When it comes to crystal shape, calcite forms flat, rhombohedral crystals, kind of like poker chips. Dolomite, on the other hand, doesn't have that distinct shape. Now, looking at the acid reactions, calcite reacts pretty strongly when you apply acid, with noticeable fizzing. Dolomite reacts much more weakly, with less affections. As for hardness, calcite has a hardness of 3 on the Mohs scale, which means it's relatively soft. Dolomite, though, is a bit harder, with a hardness between 4 or 4.5. Finally, let's talk about crystal faces. Dolomite crystals can have slightly curved faces due to their internal structure, while calcite usually has smooth, flat faces. This is the table comparison of calcite and dolomite. Next one is EDS spectrum, which give us key insight into the composition of the sample, suggesting that the mineral is dolomite and how we did this. Starting with point 1, here the point 1, the EDS spectrum shows nearly equal amounts of magnesium. You can see here. And calcium. This is a strong indications that the mineral is dolomite because its chemical formula is calcium, magnesium, CO3, 2, meaning it contains equal amount of calcium and magnesium. So, the presence of these two elements in similar proportion is a clear match for dolomite. Next, we see the presence of silicon, aluminium, and potassium here in the spectrum. These elements are typically found in silicate minerals, but in this case, they aren't a part of the dolomite itself. Instead, they are most likely coming from the silicate substrate beneath the dolomite sample. This tells us that while we're analyzing dolomite, the substrate is contributing additional elements to the spectrum. Finally, at the point 2, the spectrum shows a strong silicate composition, confirming that we are dealing with silicate minerals in the surrounding area. This further helps us separate the dolomite from the silicate substrate and reinforces our interpretation of the sample. By looking at the EDS data in this way, we can be confident that the mineral in question is indeed dolomite, and the other elements are likely from the substrate rather than the dolomite itself. Okay, let's move to another samples. To determine whether the samples contain calcite, let's break down the evidence step by step. Presence of key elements calcium, carbon, and oxygen. All three samples in E21, E23, and E24 contain calcium, carbon, and oxygen, which are the essential components of calcite, calcium CO3. This is a strong indication that calcite is present in these samples. However, we notice that E23 and E24 show no significant amount of magnesium, which suggests they are more likely to be pure calcite rather than dolomite, because in dolomite we have magnesium, which contains both calcium and magnesium. Magnesium in sample E21. For sample E21, we see the presence of magnesium in K layer. This could mean a couple of things. Either magnesium is partially substituted calcium in a calcite-like structure, or E21 could contain another magnesium-bearing mineral alongside the calcite. This is important because it means E21 might not be pure calcite, but could instead be a mix of calcite and some other mineral with magnesium content. Different calcium concentration in E23 and E24. Okay, I wrote the E23, E24, but in the picture is E40, E41, E42. Okay, the difference calcium concentration in this here and here. We see a difference. The variation suggests that this sample might have differences in mineral composition, grain size, or crystallinity. Specifically, a higher calcium concentration in E41 could indicate a greater abundance of calcite in that sample, supporting the idea that another one has more pure calcite compared to the first one. Crystal morphology. Looking at the crystal structure, we find that the small and irregular calcite crystals are consistent with how calcite forms naturally in various geological environments. This matches the expected appearance of calcite, further supporting its identification. To wrap up, based on the elemental composition, calcium, carbon, and oxygen, and crystal morphology, we can conclude that these samples are most likely calcite. However, the sample where you look the magnesium and you see the sample with consisting of magnesium might be a bit more complicated. It could either be impure calcite or a mixture of calcite and another magnesium-bearing mineral. To summarize, EDS analysis is a key tool for identifying minerals. It helps distinguish calcite, which consists only of calcium carbonate, from dolomite, which consists both calcium and magnesium. This difference is important in fields like geology, construction, and material science because it affects how these minerals are used, such as in building materials or steel production. It has not only identified these minerals but also reveals details about their composition and morphology, offering a deeper understanding of their formation. In conclusion of this presentation, thank you everyone for attention. And now let's dive into 10 questions based on this presentation.
Thank you for this good presentation. We will have like 2 minutes break until the attendees fill the feedback forms that I will send in the chat box right now. There was a problem with the feedback link and I fixed it right now. You can open it again and it will be working fine.
As I see the Azim, can you ask the information about calcite? After the presentation, do you understood everything? Or do you have some questions, maybe? Because when you need to distinguish calcite and dolomite, in this case, you need to understand how to distinguish them. That's all.
Okay, you can write your questions in the chat box or just raise your hand and I will enable the mic for you. Okay, so any more questions? Okay, great. I think we don't have any more questions. Thank you, Ms. Tilly, for this great webinar. It was really fruitful. And thanks to all attendees for attending this webinar. And see you soon, inshallah, in our next webinars. And don't forget to fill in the feedback form. Thank you, and see you soon, inshallah. And also, please note that certificates of this webinar will be generated automatically on our website. Tomorrow, they will be available on the webinar page. Thank you.
Thank you very much. Should I open the questions or it's not important?
Should you open what?
The questions which I created or not?
Yeah, sure.
Okay, fine.
I thought that you finished.
I have created a little.
Okay, sure, you can share it.
Yes, the questions, and they're not so hard. So the first question, do electron microscopy use optical lenses? You can write down your answer or just can raise your hands and answer just by using your microphone. The correct answer is electron microscopy do not use traditional optical lenses as they operate using electron beams instead of visible light. As I mentioned in the beginning of my presentation, I said that the electron beam cannot pass through the glass. That's why instead they use electromagnetic lenses, which generate magnetic fields to control and focus the electron beam. These lenses are crucial for focusing the electrons and achieving high-resolution imaging. In scanning electron microscopy SEM and transmission electron microscopy SEM, these electromagnetic lenses play a vital role in controlling the trajectory of the electron beam to create detailed imaging of the sample. Okay, next question is, What does EDS stands for? Just the meaning. What does EDS stand for? Okay, fine. Hey guys. Okay. Thank you everyone. I finished. Have a good day or evening.
Okay, thank you everyone for attending, and thank you again, Ms. Tilly, for this great webinar. I remind you again to fill the feedback form, please. So thank you and see you soon.
Thank you very much. Goodbye.